So the work that's going on in my group right now is that we really want to run up to 8 or 10,000 cores, but in an arbitrary 3D geometry that we can subdivide into slices like this. So we can take a cubic domain and subdivide it. And that is starting to work now. So Suni Lee is building that in my group, where he has shown that he can scale a cubic device simulation domain of 44 nanometer in a cube up to some 10,000, hold on, this is going to 2,000 cores. If you wanted to do this in NEMO3D as we had it before, you would be stuck up to 80 cores. You couldn't parallelize this to more than 80 cores because you couldn't do more than 80 slices like this. But now we can slice this in 2 and 3 dimensions, and it scales very nicely. That means, down the line, rather than running for 10 hours on 64 CPUs, we can run in an hour on 640 CPUs. We can run for 10 minutes in 6,000 CPUs. And you might say, well, you're out of your mind, you don't have access to these machines. We do. We do have access to these machines. We have access to 3 of those machines. And we run on those on a day-to-day basis. And computing services at these sites love us because we have a scalable code. It actually utilizes that machine nicely. Okay? We can really utilize large computing resources. Now, what would you do with a huge calculation of say, 50 million atoms, and how do you know you're getting the right result? So I'm going to show you a numerical experiment where I want to prove to you we get the right result. So we start out with a small quantum dot, like this, in a small domain, and it has only 300,000 atoms in it. Okay? So we compute the ground state, the excited states, and here are sort of the slices. Okay? Now if we take the same quantum dot and make the box around it bigger, nothing much should happen, right? I mean, it's still the same quantum dot. And indeed, if we make that box that surrounds it bigger to, say, 6.7 million atoms, the dot gets smaller because I have a bigger domain, right? The wave function plot gets smaller, but the dot doesn't get smaller. And I find the right symmetry of the states. If I make my domain even bigger still to 21 million atoms, I can still peel out the right eigenenergies of the system. What is challenging about that is that we are interested in identifying energies, eigenenergies, that are in the middle of the spectrum, right? We're at minus 20 eV, we have eigenvalues, and then a whole lot of eigenvalues, and ending up at plus 20 eV. But we want to get the ones that are interior, in the middle of the spectrum. Okay? Most eigenvalue solvers do well on the exterior ones, not on the interior ones. So this slides really demonstrate that we can get unique and targeted eigenstates of the correct symmetry for all these structures. So now that we can do this on a day-to-day basis, what we have been doing is really that we have a capability to have arbitrary 3D zinc blende and Wurtzite crystals. We can have strain and valence force fields. We can have piezoelectricity through potential perturbation. And we can have electronic structure with empirical tight binding. We can apply this now for indium gallium arsenide quantum dots, for valley splitting in silicon, alloy disorder in bulk, quantum dots, nanowires, and single impurities in silicon. So these are going to be in the subsequent lectures on how we utilize a tool like that to answer interesting questions that you couldn't answer really any other way. All right? Any questions? Yes?
I would have a lot of questions on this stuff. It's very interesting. But the first one is about the problem of using ab initio codes that obviously are not suitable for medium atoms. They are not even suitable for thousands of atoms. So, but for the optical properties, there are some problems. So it does, like, especially for very small one like excitons or excited system response that in some cases, like cyclone small cluster, can be huge difference. For example, the energy gap between the ground state and the excited system and stuff like this. So I would like to know what are the limitations and the most huge limitation to solve now with the empirical turbine application for
okay. So I'm not completely sure. So let me repeat the question as I understood it, and then you can tell me. No, let me repeat the question. So if I understood the question right is, what are the limitations of tight binding with respect to model excitons and disorders that may be locally dependent due to clustering of material?
Well, yeah, not so consistent structure, let's say.
Okay, got it. And then structure, making sure you get the right structure. So let me start with the downfalls of tight binding, the way we do it. We guess the structure, right? We guess how the atoms are connected and who is connected to whom, and then we do a valence force field relaxation to minimize the total strain energy in the system. So the guys can move around, but they can't change order and go, I'm going to over here and you come over my place, and therefore we minimize the total energy, right? So we don't do a true relaxation in the thermodynamical sense where bonds can change and all that. Also, if we can do excitons in principle as a perturbation approach. So if we calculate the eigenstates of our system, we can then calculate direct and exchange matrix elements for excitons, and we do that. Those are the fundamental things we can do towards that realm. Okay?
Let's say for the industry, for like properties of protein nodes, are also emission methods a way to run, or it's something that's...
I don't think so.
Out of
well, unless they're colloidal dots that have 1,000 atoms in it, I think you're out of the ballpark. But I'll show you in the next presentations how we can nail experimental data on a 9 million atom system. Okay? Okay? So it's 1:15, you guys are getting glazy eyes. That means we should do 3 more lectures, right? So